Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Ghesya Arnellia Brilian with last ID number 29. In here, I will explain to you guys about Deadlocks. It is an operating system materials. Okay, first of all, what is Deadlocks? We all deadlocks, but what is deadlocks? In a multi-programming environment, several threads may compete for an infinite number of resources. A thread requests resources. If the resources are not available at that time, the thread enters a waiting state. Sometimes a waiting thread can never again change state because the resources it has requested are held by other waiting threads. This situation is called a deadlock. So as we can read in the screen, it's something that help something. Okay, for next one. Here are the materials that will be explained inside this video. For first of all, there is system model. Second, deadlock and multi-threaded application. Next one is deadlock characterization. And next, methods for handling deadlocks, deadlock prevention, deadlock avoidance, deadlock detection, recovery from deadlock, and the last one is summary. Okay, let's start with the first one. It's system model. A system consists of a finite number of resources to be distributed among a number of competing threads. The resources may be partitioned into several types, or we can say classes, each consisting of some number of identical instances. Under the normal mode of operation, a thread may utilize a resource in only the following sequence. The first one is request. The thread requests the resource. If the request cannot be granted or cannot be granted, you can say, immediately as fast as it could. For example, if a mutex lock is currently held by another thread, then the requesting thread must wait until it can acquire the resource. So the thread must wait. The second one is use. The thread can operate on the resource. For example, if the resource is a mutex lock, the thread can access in critical section. And third one is release. Thread release the resource. Okay, move to the next one. It's deadlocks in multi-threaded application. For the first one in deadlocks in multi-thread application, we all know something called leaf lock. Leaf lock is another form of witness failure. It is similar to deadlock. Both prevent two or more threads from proceeding, but the threads are unable to proceed for different reasons. Whereas deadlock occurs when every thread in a set is blocked, waiting for an event that can be caused only by another thread in set. Leaf lock occurs when a thread continuously attempts an action that fails. Leaf lock typically occurs when thread retry failing operations at the same time. It thus can generally be avoided by having each thread retry the failing operation at random times. This is precisely the approach taken by Ethernet networks when a network collision occurs. Rather than trying to retransmit a packet immediately after a collision occurs, a host involved in a collision will back off a random period of time before attempting to transmit again. Leaf lock is less common than deadlock, but nonetheless is a challenging issue in designing concurrent applications. And like deadlock, it may only occur under specific scheduling circumstances. Okay, for the third one is deadlock characterization. There is necessary condition. A deadlock situation can arise if the following four conditions hold simultaneously in a system. For the first one is mutual exclusion. At least one resource must be held in a non-shareable mode. That is, only one thread at the same time can use the resource. If another thread requests that resource, the requesting thread must be delayed until the resource has been released. For the second one is hold and wait. A thread must be holding at least one resource and waiting to occur additional resources that are currently being held by other threads. The third one is no preemptions. Resource cannot be preempted, that is, a resource can be released only voluntarily by the thread holding it, after that thread has completed its task. The fourth one is circular wait. A set T0, T1, blah 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 Tn of waiting threads must exist such that is T0 is waiting for a resource held by T1. T1 is waiting for a resource held by T2, and so go on until Tn minus 1 is waiting for a resource held by Tn, and Tn is waiting for a resource held by To. So it's moved like a circular. Here are the example for resource allocation graph. Like you can see in the picture below, where the first one is the picture of resource allocation graph, and the second one, in the middle one, resource allocation graph with a deadlock, and the third one is resource allocation graph with cycle but no deadlock. There are several differences in the picture, and you can see what kind of differences and where each lines line up. Next one is methods for handling deadlocks. We can deal with the deadlock problem in one of three ways. We can ignore the problem altogether and pretend that deadlocks never occur in the system. We can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlock state. We can allow the system to enter a deadlock state, detect and recover. Ensure that the system will never enter a deadlock state. First one is deadlock prevention, and the second one is deadlock avoidance. Okay, for the first one, we can continue with deadlock prevention. There is mutual exclusion. It is the mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources do not require mutually exclusive access, and this cannot be involved in a deadlock. Read-only files are a good example of a shareable resource. If several threads attempt to open a read-only file at the same time, they can be granted simultaneous access to the file. A thread never needs to wait for a shareable resource. In general, however, we cannot prevent deadlocks by denying the mutual exclusion condition, because some resources are intrinsically non-shareable. For example, a mutex lock cannot be simultaneously shared by several threads. Okay, move to the next one is hold and wait. Hold and wait. An alternative protocol allows a thread to request resources only when it has none. A thread may request some resources and use them. So in here we can know that a thread can request some resource for them to use it. Okay, before it can request any additional resources, it must release all the resources that it is currently allocated. Both these protocols have two main disadvantages. For the first, resource utilization may be low, since your resource may be allocated but unused for a long period. For example, a thread may be allocated a mutex lock for its entire execution, yet only require it for a short duration. And the second one, starvation is possible. It is possible for them to starvation. A thread that needs several popular resources may have to wait indefinitely, because at least one of the resources that it needs is always allocated to some other thread. The next one is no preemption. So what is no preemption? If a process that is holding some resources requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. Preempted resources are added to the list of resources for which the process is waiting. Process will be restarted only when it can regain its old resources, as well as new ones that is requesting. Okay, the next is circular wait. Impose a total ordering of all resource types and require that each process request resources in an increasing order of enumeration. Here is the example of deadlock example with lock ordering. Here is the code. The next one is deadlock avoidance. Like we have talked about before, that there is a deadlock avoidance. We can deal with the deadlock problem in one of three ways. We can ignore the problem altogether and pretend that deadlocks never occur in the system, or so on like before. Okay, for the next one, it'll talk about safe state. Okay, a state is safe if the system can allocate resources to each thread up to its maximum in some order and still avoid a deadlock. More formally, a system is in a safe state only if there exists a safe sequence. A sequence of threads is a safe sequence for the current allocation state. If for each TI, the resources requests that TI can still make can be satisfied with the currently available resources, plus the resources held by all TJ with J less than I. Like in the picture here, here is the example of safe, unsafe, and deadlock state spaces. Okay, here is some notes. If a system is in safe state, then there is no deadlocks. If a system is in unsafe state, possibility of deadlock. Avoidance ensure that the system will never enter an unsafe state. Okay, for next one, avoidance algorithms. Single instance of a resource type use a resources allocation graph, and multiple instances of a resource type use the banker's algorithm. And the next one is resource allocation graph SIM. First one, claim HPI indicated that process PJ may request resources RG represented by a dash line. Second one, claim H converts the request H when a process requests a resource. Third one, request H converted to an assignment H when the resource is allocated to the process. Fourth one, when a resource is released by a process, assignment H converts to a claim H. The fifth one, resources must be claimed a priori in system. Here's the example of resource allocation graph for deadlock avoidance and an unsafe state in resource allocation graph. Here are the pictures to make the imagination and explanation more can be understand more. Okay, so there is a resource allocation graph algorithm. Suppose that process PI requests a resource from RJ. The request can be granted only if it converting the request H to an assignment H does not result in the formation of a cycle in the resource allocation graph. Okay, next one is Banker's algorithm. There is multiple instances. Each process must a priori claim maximum use. When a process requests a resource, it may have to wait, and when a process gets all its resources, it must return them in a infinite amount of time. There are viable factor of length, like here in second on the side here are some like about available max allocation and need explanation of it, and so many like explanation like that. Okay, and here is safety algorithm. First network and finish vectors of length m and n respectively initialize work equals with available finish I false for I equals 0, 1, and etc. Second one, find an I such that both a finish I equals false. Need E work. If no such I exists, go to step 4. Step 3, work equals work plus allocation E. Finish I equals true. Go to step 2. And for the step 4, if finish I equals true for all I, then the system is in a safe state. Next one is resource request algorithm. Request I equals request vector for process pi. If request I, j equals k, then process pi wants k instances of resource type rg. If request I init I go to step 2, otherwise raise error condition since process has exceeded its maximum climb. Second, if request I available, go to step 3. Otherwise, PI must wait since resources are not available. Step 3. Pretend to allocate requested resources to PI by modifying states as follows. Available equals with available minus request I. Allocation equals allocation plus request I. Need I equals need I minus request I. If safe, the resources are not allocated to PI. If unsafe, PI must wait, and the off-resource allocation state is restored. Okay, move to the next one is deadlock detection. If a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may occur. occur. In this environment, the system may provide, first one, an algorithm that examines the state of the system to determine whether a deadlock has occurred or not. And second one, an algorithm to recover from the deadlock that has occurred. Single instance of each resource type. The first one, maintain wait for graph. Nodes are processed, PI or PJ, if PI is waiting for PJ. B, or we can say the second one, periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, there exists a deadlock. And the third one, an algorithm to detect a cycle in a graph requires an order of n2 operations, where n is the number of vertices in the graph. Here is the picture for the example of resource allocation graph and corresponding wait for graph. Several instances of resource type. Okay, first one is available. A vector of length m indicates the number of available resources of each type. Second one is allocation. An nxm matrix defines the number of resources of each type currently allocated to each process. The third one is request. An nxm matrix indicates the current request of each process. If request ij equals k, then process pi is requesting k more instances of resource type rg. Again, its detection algorithm. Let work and finish with vectors of length m and n respectively. Initialize work equals available for I equals 0, 1, etc. until n minus 1. If allocation equals 0, then finish I equals false. Otherwise, finish I equals true. Find an index I such that both finish I equals false, b request I less than work. If no such I exists, go to step 4. Work equals work plus allocation finish I equals true, go to step 2. If finish I equals false for some I, 0 less than I. And moving again, recovery from deadlock. So what it is again? Well, a detection algorithm determines that a deadlock exists. Several alternatives are available. One possibility is to inform the operator that a deadlock has occurred and to let the operator deal with the deadlock manually. Another possibility is to let the system recover from the deadlock automatically. There are two options available. Well, the first one is process and thread termination, and the second one, resource preemption. But what are they? So process and thread termination is first one, abort all deadlock process. This method clearly will break the deadlock cycle, but at great expense the deadlock process may have completed for a long time, and the results of this partial completion. The second one is abort one process at a time until the deadlock cycle is eliminated. This method incurs considerable overhead since after each process is aborted, a deadlock detection algorithm must be invoked to determine whether any processes are still deadlocked. In which order shall we process to abort? First, priority of the process. Second, how long process has completed and how much longer to completion. Third, resources the process has used. 4, resources processes needs to complete. 5, how many processes will need to be terminated. 6, is process interactive or batch? Okay, continue to resource preemption. The first one is selecting a victim, minimize cost, and second, rollback, return to some safe state, restart process for that state, and third one, starvation. Some process may always be picked as victim, include number of rollback in cost factor. Resource preemption when and how often to invoke depends on some like above here. And for the second one, if detection algorithm is invoked arbitrarily, there are maybe many cycles in the resources graph, and so we would not be able to tell which of the many deadlock processes caused the deadlock. Okay, in summary, deadlock occurs in the set of process when every process in the set is waiting for an event that can only be caused by another process in the set. And another story, there are 4 necessary conditions for deadlock: mutual exclusion, hold and wait, no preemption, and circular wait. Deadlock is only possible when all 4 conditions are present. Deadlocks can be modeled with resource allocation graphs where a cycle indicates deadlock. Deadlock can be prevented by ensuring that one of the four necessary conditions for deadlock cannot occur. Of the four necessary conditions, eliminating the circular weight is the only practical approach. Deadlock can be avoided by using the Penger's algorithm, which does not grant resources. In doing so, would lead the system into an unsafe state where deadlock will be possible. A deadlock detection algorithm can evaluate processes and resources on a running system to determine if a set of processes is in deadlock state. If deadlock does occur, a system can attempt to recover from deadlock by either aborting one of the processes in the circular wait or preempting resources that have been assigned to deadlock process. Okay, that's all from me. Thank you for watching. I hope this will be helpful for every of us. That's all for me. Wassalamualaikum warahmatullahi wabarakatuh.